Hello and welcome to the Switch List. My name is Rick and this is my YouTube channel where my goal is to chronicle my journey as I re-enter the world of model railroading after a couple of decades away. I hope that you enjoyed this video, and if so, please consider giving it a thumbs up as well as clicking the subscribe and the little bell icon so you can be notified of any future videos. Hello everyone. In this video I plan to show you my take on building a Arduino based speedometer for your model railroad. Now, a little bit of history and how this video got started is after getting into the hobby last year, I was at the Burlington County Model Railroad Club and we were running trains there, and somebody pulled out one of those commercial speedometers and I thought, hey, that is pretty slick, and I thought, you know, that probably wouldn't be too difficult to build one of your own rather than buy it, and that'd be kind of a cool project. And I was pretty sure that I had an Arduino somewhere in a box somewhere that hadn't been pulled out for a couple years. And so it started kicking around in my mind, but I knew I didn't have a sensor. I figured I had LCD, I had the Arduino, I had everything else I needed, but I didn't have any sensors. So I'm thinking about it, but I hadn't moved forward. And then Joe G over at his channel published a video probably over a month ago now where he showed how he took an Arduino speedometer and he integrated it into his layout, and that's a really great video that I highly recommend you all go check out. I will put a link in the description down below and maybe a card up here if I can figure out how to do that correctly. So go over there and take a look at it. He provides the information on where to get the sensors and the Arduino and everything. The link to the sensors, I use that, I ordered them. It comes in a bag, and there's 10 of them. And so I used those, and I went ahead and started putting this video together after sending an email or leaving a message to Joe on his channel about how he beat me to getting this video done. And he told me it took him like 2 years to get the video done, so I'm hoping that I'll be a little bit quicker. And his video was really interesting in that it focused on actually not so much the speedometer itself, but how to integrate it into the layout and hook it all up, and showed you all the pieces and the wiring and stuff. So again, take a look at that. This video is really a little bit more focused implementation, and this is, in my vision, this is video 1 of 2. The first one I'm just going to show you the prototype, which is built up on the Arduino itself. It has I used a keypad shield that I had already in my inventory, so it's a very small display, not as big as the nice one that Joe used. I only have 2 lines by 16 characters, so there's not a lot of space, but you'll see what I was able to accomplish. And part 2 of this, I want to take it to the next level based on some conversations that I had with guys at the Burlington County Model Railroad Club. And I'm not going to give anything away here on that, but I think that one is really going to be cool. But I at least wanted to get this one out and say, see there, Joe, I got it done. And again, I thank him for the inspiration and for encouraging me to go ahead and do this, even though he did one just recently, and I'm sure there must be many, many more out there. So anyway, sit back, enjoy as we take a look at putting together an Arduino-based speedometer. And if anybody is interested in the code that I used, please just feel free to send me a message and give me an email address, and I will be happy to send the code that I created for that if you want to try and replicate it or take it and make some changes and make it even better. All right, well, give me a minute and we'll move over to the workbench and we'll get started. Okay, so what are we going to need to make this happen? So let me put that aside for a second. Let me pull out the old box of goodies here. As far away as I can be. Alright, so let's see what we got in here. We got some spare Atmega 328 chips. Okay, here we go. We got the Arduino. We're going to need that. And this is the LCD keypad shield that I'm going to be using. This is just an LCD. It's got some built-in buttons on it, and it plugs right onto the Arduino, and it makes life easy for doing some simple development with an LCD screen. Of course, the main drawback is this one is only 2 lines by 16 characters, so we're going to get creative on putting the information that we need in there. We're obviously going to need some of the hookup wires as we connect different things. We are going to need a breadboard. Let me pause a moment and get the breadboard, which use a little breadboard here. And then the last thing we need, so these are our Arduino parts, and then the last thing that I mentioned in the intro, we need the sensors, and these sensors are ones that I ordered based on the link over at Joe G's channel, so we go take a look at that and get the information. If I remember, I'll put a link in it myself. So You order these, and I forget what they cost, not too much, and you actually get 10 of them. As you can see, there are only 8 here, and that's because I've already used 2 of them to put the speedometer together. So once again, as always seems to be my way, I am making a video after the project is done. So anyway, but we will walk through what I'm doing here. So I'm going to take 2 of these sensors, and these are just simple infrared sensors. They have one of them is the emitter and one's the detector, and anytime it detects the reflection, then you get an output signal indicating that the sensor's been triggered, and we'll talk through that. So if you watch Joe G's channel, he simply took and he soldered. If you can see here on these have got these little pins, and he just simply soldered wires onto each of those. And you can see, I can figure out how to work the camera. You have VCC, which is your plus 5 volts on the right side, ground in the center, and then the output signal from the sensor is this 3rd pin here. And that signal will go low whenever it will go from 5 volts down to 0 volts whenever you've triggered this sensor. So as I mentioned, Joe went ahead and he soldered wires onto this. But what I'm going to do is I'm actually going to remove these and remove these connectors and solder some wires into this directly. I'm going to pull these out, and then I'm going to go ahead and solder some wires in there. Okay, to start off, I'm going to I've got my 3 spools of wire, red, green, and black. Red will be 5 volts, black will be ground, and then green will be my output signal. So I'm going to take and just get off a reasonable length. I'm going to cut them all even. Okay. Out of the way. And now what I want to do, try not to bang the camera, is come in here and actually strip each of these down. And of course that's the one. Okay, nothing like a automated sales call in the middle of trying to make your YouTube video. So again, I'm back. I'm going to go and I'm going to strip off the ends, a little bit off each one of these. Okay, I've got the end of each of the 3 wires stripped. I'm also going to use some paste flux here. I'm going to get my 3rd hand out here. So I'll use this just to use these alligator clips to hold the wires so I can keep them from moving around on me as I do it. So first thing I'll do is I'll just dip these in there, get some flux on them, clamp them in there, and now I'm going to go ahead and tin each of them. There's a couple of different ways I can go about removing these pins. I think the best thing I want to do, because these are all hooked together, and that would mean if I was going to try to just heat these up and pull them out, I'd need to get all 3 of them heated up to the same temperature so that the solder would melt and I could pull them out. So what I'm going to do is I'm going to go ahead and just cut off the bent portion here, and that should allow me to either just pull the black plastic that connects them off, or I can just snip this in between so that they're separated. So now they're individual. So now what I should be able to do is just come in here, grab the first one, heat up the solder here. Hopefully with a little luck there, just pull it right out. So now we'll go on to the next one. There we go. And then finally the 3rd one. Alright. Now, I don't know if you can see it, but the holes are full of solder, so we're going to need to clean that up. So hopefully I'll be able to just use my desoldering tool here. What I'll do is try to heat this from the back, and then this might take a couple tries. Okay, I was finally able to get those holes cleaned out. So now what I'm going to do is I'm going to put the red wire in the VCC, the black wire in the ground, and the green wire in the out. Oh, that one's a little too much solder on it, so let me just cut it down because it's too long as well. So, okay. Alright. So there you go, you can see I've got the 3 wires in there. And so now what I'll do, just go ahead and solder those down. And check them to make sure they got good joints. The green one I'm not happy with, so let me touch that up. Okay, that's better. Now I'm going to go ahead and cut these off. Nice and flush. And I'm going to check them with the magnifier here to make sure that I don't see any shorting. Okay, so there you have it. We've got the first one done. And I'm going to go ahead and do the second one real quick, and then we'll be back. Okay, we've got them both done. And as you can see here, I took and I used a little wire tie here just to kind of keep the wires under control. So we've got the sensors, they're ready to go, and let's pull out the Arduino and the LCD keypad shield, and these just connect together like this. And what we're going to need to do now is connect it, make it ability so that we can connect the Arduino to the sensors. So what I'll do is I will connect the Arduinos, the sensors, into the breadboard. I'm going to use the plus and minus rails on the breadboard, and then I will just stick this sensor here, and I will do the opposite over here. So positive, negative, and oops, I think I don't have enough wire on the negative, so give me 1 second, I'll be right back. Okay, got that in. So let me bring this in closer, and hopefully you'll be able to see that on the very outside is the positive rail, so that runs all the way along here, and then the next one up is the negative. So those are all connected. The negatives are all connected, the positives are all connected, and you have another one here. Now they aren't, the up here and down here is not connected internally, so I'd have to run a wire to bring if I wanted to use this side here. And then these are, these rows are connected, all these are connected, but they're not connected to the next one over, so these are, so, okay, so what I'm going to do now is I'm actually going to connect this up to the Arduino, and I'm going to use some of these wires. So the first thing I want to do is I'm actually going to take power from the Arduino to power the sensors. So what I'm going to do here is I'm going to get a red and a black wire, and I'm going to go this way to make it easier. So right here is a 5-volt connection on the Arduino, so I will plug that into my 5-volt rail, and right next to it is a ground connection, so I'll plug that in, plug that into the ground, and then I need to connect the sensors. Now I'll use a green wire to keep consistency here. That's really not long enough. That's some longer green wires. Nope, I'm going to have to go with orange wires, I guess. Alright, maybe I can maybe I can fudge this a little bit. So the way I have this, I'm setting this up is I'm going to use the 2 interrupt pins on the Arduino. So rather than sitting there in the loop in the Arduino simply checking the pins to see if there's been a change, I'm actually enabling interrupts, which basically tells the Arduino that anytime it detects a change on the pin, I want it to generate an interrupt, which means go run a special routine tied to the interrupt of that pin and run some code there and then return. So the loop doesn't constantly monitor the pins, but anytime a change occurs, it's detected and the Arduino processes the appropriate, what's called an interrupt service routine, and that's the code tied to running, that's designed to run whenever there is an interrupt detected. All right, I'm going to try and see if I can find a much longer wire to kind of try to keep them out of the way here. Alright, it's not much longer, but at least it'll make it easier. Okay, so hopefully. Now what I need is a way to power the Arduino. Okay, so I've grabbed a wall wart that's going to allow me to power the Arduino as well as the sensors here. Let me see, I'm going to try and get this. So let me plug this in. And I don't know if you'll be able to read that on the screen. But what you can see here is the red LEDs indicate that the sensor's got power. The green indicates that it's being triggered, and the reason it's being triggered is because of all of this ambient light. Now if I turn these off, and I may still, there we go. So now you can see, hopefully you can still see the green one off. And if I come in here, and let me do it this way, put my finger in front of it, you can see that it triggers. What I can do here is, let's just say I trigger the first one, and it says busy, and then I come over here and trigger the second one, and it said it was 4.5 miles an hour, which of course doesn't make a whole lot of sense since I need to have it mounted. So let's go over to the layout, mount this. I'm going to mount this up and we'll do a little demonstration of it and then discuss it some more. I'll be right back. I decided that before we jump right into looking at the speedometer running on the layout, we ought to spend a couple of minutes taking a look at the code. And I'm not going to delve too deep into this, but I did just want to touch on a couple of ideas. And so before we start here with the actual code, I'm going to bring up a flowchart. So here's a flowchart that explains how the code is working. And we're going to start here on the left. This is the main sketch and what people typically used to seeing when it comes to an Arduino sketch. So it starts up. The very first thing we're going to do is we're going to load any external libraries or include files that we might need. We define the constants that are used by the program, and then we create our global variables. These are variables that can be read from and written to by any function in the program. And what you can see here is anything in these orangish blocks are functions. So there's the setup function and the loop function, which pretty much every Arduino sketch has those two. And in some cases, those may be the only two. But you can have additional functions. In this case, I have something here called Sensor 1 ISR and Sensor 2 ISR. ISR stands for Interrupt Service Routine. And we'll talk about that in just one second. So after we create our global variables, we come in here, we do the setup of where we initialize all the I/O pins, we initialize the LCD screen, and we initialize variables, any of the global variables that we want to set up ahead of time. Then we drop into the loop, and in this loop we do three main things. We check to see if the mode button has been pressed. The mode button allows the user to select between N scale and HO scale to display the speed. We check to see if the op state flag has been set to busy. The op state flag is the flag that indicates that we are actively acquiring data for a measurement. So, and you'll see that variable gets set by the interrupt service routines, but they don't actually update the display. So what we do here is we're checking to see if the op state flag has been set to busy, and if it is, then we update the LCD screen to say that we're busy. And then the third thing we do, which is the meat of the loop function, is check if the speed measure flag. The last thing we do is we check if speed measure flag
or the update speed display flag has been set to true. The speed mesh flag gets set to true by the interrupt service routines when they determine that a train has passed both sensors and there's data available to calculate the speed. And the update speed display flag is set in the up here in the check to see if the mode button is pressed. If the user presses the mode button, and if there's existing speed data on the screen, then this flag will tell us to go ahead and update the display to display the speed. And then that's all the loop does. Just sits there, does those three things over and over and over. The interrupt service routines, the way I've done this is I have tied sensor 1 to interrupt 0 of the Arduino and sensor 2 to the interrupt 1 of the Arduino. So the Arduino Uno has two interrupt enabled pins, pins 2 and 3. We configured those pins to generate an interrupt that basically says, or when the sensor gets triggered, go run a specific routine function. And so we have sensor 1 ISR function and we have the sensor 2 ISR. So anytime sensor 1 triggers, it runs this code. Anytime sensor 2 triggers, it runs that code. These are identical with the exception of direction. So what we see here is when we detect the sensor has been triggered, we capture the current millis value. Millis is just a counter that counts every 1 millisecond, every 1,000th of a second, it increments 1. So so this is the way in which we capture the time between sensor 1 triggering and sensor 2 triggering. And we store that value in a variable called sensor 1 trigger time. Next, we check to see if the current op state is ready. If the current op state is ready, that means the speedometer is sitting there waiting for a trigger. And if the op state is ready, then this trigger that has occurred is the start of a train coming through the speedometer. So what we want to do is we set the op state to busy, because we're now in the process of capturing data. We save the sensor 1 trigger time that we captured up here into a start time variable. So start time indicates the time when we entered the speedometer, and we'll have an end time variable that indicates when we've left. So we save that value in start time, and then we set the train direction to eastbound, and then exit the interrupt service routine. Eastbound is simply defined by sensor 1 is triggered first, sensor 2 is triggered second. So you'll see down here in ISR2, everything is the same. So that's what occurs if the op state is ready when we're in the interrupt service routine. Now, if the op state is busy, so now it must be busy. So now we say, okay, it's busy. Now we want to check to see if the current direction is eastbound. If it is eastbound, otherwise, if the op state is not ready, so it's busy, then we want to check the direction of the train. And if it's eastbound, we don't need to do anything, and we just exit. And this is in here just in case we have, for some reason, there's a false trigger on the first sensor, or a variation in the lengths of the cars may cause this to trigger. So we just want to ignore that if we're already eastbound. So otherwise, if it's not ready and we're not eastbound, then a trigger on this sensor indicates the end of the capture, right? So we're going to save the sensor 1 trigger time that we captured at the very beginning into the end time variable, and set the speed mesh flag to true and exit. So this right here is what tells the main loop, okay, we have data, we need to calculate it. And again, the same thing here, except we're going to set the direction to westbound if the op state was ready. Otherwise, if it was busy, we check to see if it's westbound and we exit if it is. Otherwise, it's not westbound. So this is now the second sensor, and we will save the sensor 2 trigger time into end time and exit the ISR. Okay, so that's just the basic flow of how this works. So now let me bring up the actual code, and we'll take a quick run through it. Here's where I've included the one library that I need, which is the liquidcrystal.h, so that I can talk to the LCD button shield that I'm using. My program constants, if you're not familiar with the way that this works, some people will just define an integer. They'll say, int sensor 1 pin equals 2. But by doing that, you're creating a variable which uses up program memory, which you don't want to do. So in this case, a pound define simply says, when we go to compile the sketch, the precompiler will go through and say everywhere that it sees sensor 1 pin, it will substitute this, the number 2. So now we can refer to it within our code with this human readable value, but we will let the preprocessor go ahead and convert that into the numeric values, and we don't use up any memory. And I did a quick check when I was writing this, and by doing it this way, I saved 48 bytes of program storage space versus defining each one of these as an integer value, for example. So we have our 2 sensor pins. We have the mode pin. This is where the button is attached to change the mode between HO and N. I've defined the 2 ratios for HO scale and N scale. Sensor spacing in inches is 3. The ready state, I've defined ready, busy, eastbound, westbound, and then a wait time. The wait time is how long there has to be no trigger on the exit sensor before the system will reset and go back to the ready state. The last thing is a little bit different you may not have seen before. Here I'm simply doing a pound define debug, because all of these up here, we have pound define, what you're defining, and the replacement value. In this case, there is no replacement value. This is simply saying I'm declaring debug as defined. It can either be defined or undefined. So I'm declaring it as defined, and we'll see in a minute how that's used and why I've done that. Then we move into the global variable definitions. So all of our start time, end time, sensor 1 and 2 trigger times, the elapsed time that we calculate, the train speed that we calculate. We have a scale variable that's in the beginning is set to HO scale because that's how I have it set to start up. And then we have our various operating states, the op state, speed measure, train direction, and the update speed display flags. And then this is just to turn the backlight on the screen. Then the final one is this is a variable called LCD. It has a type of liquid crystal, and these are the pins that are used to interface to the LCD. So now we get into our setup function, and here you can see my first use of that pound defined debug up here. Here I'm using a preprocessor directive called ifdef. So it's saying if debug is defined, then do this code. Include this code when you compile it. Obviously, this is just a comment, but here is where I set up the serial port and I write data out to it. So this is going to allow me to, while I'm doing development, I use the serial monitor a lot to get data out of the system and understand what's going on. But once it's all done, I don't need or want that code to be compiled into the sketch and put into the Arduino. So by simply coming up here and commenting out this line here, then every time I have this ifdef and if, anything in between those will not get compiled into the sketch. It will not use up memory. So you'll see that I've used that everywhere that I do any writing to the serial monitor is going to be surrounded by these, and I'm not going to discuss those any further as I run through the code. So here I've configured the 2 sensor 1 and sensor 2 pins as input with the internal pull-up resistor. Then now this is where we turn them into interrupt driven. This digital pin to interrupt maps this pin, an interrupt on this pin, to this code. This is the name of the function that is going to run when there is an interrupt on this pin. And we've declared that in this case we want an interrupt to occur whenever there is a falling edge, which means whenever the voltage goes from 5 volts down to 0, because our sensors put out a high when they're not triggered, and they put a low 0 volts when they are triggered. So anytime we see that edge, that voltage fall, we want to trigger an interrupt on this pin. Now we just initialize the LCD. We put the splash screen on there, put the channel name. Then we say we're initializing and delay. And then we go ahead and say put ready on the screen. And then the last thing we do in the setup is we set speed measure to false because there is no speed data available. We say the update speed display is also false because no mode pin has been pressed. We clear the elapsed time variable, and we set op state equals ready. So now the speedometer is ready, and we drop into the loop. Now in the loop, as I just mentioned, there are 3 things that we do. We check the mode pin, we check the op state flag, and we check to see if there's data that needs to be converted into speed and displayed. For my buttons on this button shield or LCD button shield, you do an analog read of the mode pin, and if that value is less than 60, the mode button has been pressed. And so then If the scale is currently HO scale when the user pressed the button, then we set the scale to N scale. Otherwise, it must have already been N scale, so we'll set it to HO. We go back and we read the pin again, and if it's still less than 60, we wait half a second, and then we check it again. So this is just to debounce the button and prevent multiple button presses from being triggered as the user pushes or releases the button. Then we go ahead and we update the LCD to indicate the new scale. If the elapsed time is greater than 0, so if there's valid speed data on the display, then we're going to set the flag that says we need to update that display because we've changed it. So that's the first thing that the loop function does. The second thing is, as I mentioned, it looks at the op state flag, and if it's been set to busy by the interrupt service routine, then it will update the LCD to say busy. And then the last thing, which is where the brunt of the work is done here in the loop code, is we check the speed mesh flag and the update speed display flag to see if either one of those are true. If either one of those are true, then we need to do something on the display. So if the speed mesh flag is equal to true, then we calculate elapsed time, which was basically just done by saying the end time minus the start time divided by 1,000, because these variables are in milliseconds. So we divide it by 1,000, and you can see here that I do 1,000.0. That's what you need to do in order to force the elapsed time to come out with digits after the decimal point. If you just put 1,000, because these two variables are both integer values, then what you'll end up here is with an integer value here. We don't want that. We want to force it to give us the decimal number. We then calculate train speed, which is simply the sensor spacing, which is 3 inches in this case, and you divide that by the elapsed time we just calculated, and then you multiply that by the scale that you're using, and then finally you divide it by 17.6. And 17.6 is simply the number of inches in a mile, which is 63,360, divided by the number of seconds in an hour. So 63,360 divided by 3,600 is 17.6, and that's how you get from miles per hour to inches per second. And the last thing we're going to do is, because I want my numbers to always display with the very last digit in the last column, is I assume that the speed is going to be a number, a decimal point, and a number, so 3.2, 5.4. So I set the column number to 13. So then it would be columns 13, 14, and 15 would be used to display those three digits, and the columns are 0 to 16 on this 0 to 15 on the 16 character display. So I set it to 13. Then I check to see if the train speed is actually greater than or equal to 100. If it is, then I need to subtract 2 from the starting column to allow for those 2 additional digits. And you can see here I do this call num minus equal 2. That's the same as saying call num equals call num minus 2. This is just a shorthand notation in the C programming language. After I've checked for greater than or equal to 100, if it wasn't greater than or equal to 100, I still need to check it to see if it's greater than or equal to 10 and just subtract 1 instead of 2. And here again, call num minus minus is the same thing as saying call num equals call num minus 1. Again, another C shorthand. So once we've got the column number calculated, we can go ahead and we put the MPH tag on starting at column 6, and then we move the cursor to the column number that we've calculated on line 0, and then we put out the train speed. Now, because I display both KPH and MPH at the same time on the screen, I have to do this whole thing over again. I can't just rely on the existing column number value, because KPH is 1.61 times the miles per hour. So you could have, 80 miles per hour gives you over 100 kilometers per hour, and so that it wouldn't line up. So I have to start all over again, reset it to 13, check the kilometers per hour value for greater than 100 and subtract 2, or check for greater than 10 and subtract 1. Once we print that out, we update the display to show wait instead of ready or busy, because now we're in a wait mode. We're waiting for the sensor, the speedometer, the train to clear the speedometer. So the way that works is, depending upon the direction, the current setting for the train direction, we know what the exit sensor is, and then the code will sit there and check to see if the current time is more than 10 seconds, which is that wait time value that we defined up in at the beginning of the code. If the current time minus the last time this sensor triggered is less than the wait time that we specified, then we delay half a second and we do it again. We just sit here and we wait. So we wait for 10 seconds after the last time the exit sensor triggered before we declare the speedometer reset and ready to go. Once it's been more than 10 seconds, we set the update speed flag to false, we set the speed measure to false because we now are waiting for new data, and we set the op state to ready, update the LCD, and we're done. In a nutshell, that's how the code works. So now I'll go ahead and go over to the layout and show you the demo.
Okay, so now we're over at the layout, and you may not seen the layout previously. So this is my temporary 4x6 sheet with some Atlas Code 83 Flex track on it, just so I could get my fix of running trains around in a circle and play around with some other things. So, and you'll notice here that I'm on a different breadboard. Grabbed a bigger one that would allow me to have a little more space and be able to do this demonstration a little more effectively. You'll notice I've got the sensors mounted here on this board. Now the code is written to expect the sensors to be 3 inches apart, which is what they are here. So, and as you can see, the output of the sensors, this sensor 1 here comes down here, and then through this orange wire comes up into the Arduino, and then the same thing over here comes down and then comes up through the orange wire here. And then I've got the power and ground connected as well. So I'm going to turn on the power. You'll see the Arduino come up, say that it's initializing, and now it says it's ready and that it's in HO mode. And we'll talk about that a little bit later. I'm going to start the train up. We're going to watch it come through. We'll try to get it around, I think, 20 miles an hour. And we'll watch. It'll trigger when it hits the hopper. And then the second one, and you can see 20.3 miles an hour. You can see I've been doing this way too much lately. So, and you'll see it says wait. It's waiting for the train to clear. So as soon as what it does is every time it detects a transition on whichever sensor it is that's the outbound sensor, if you will, the second sensor, it waits for 10 seconds after the last time it triggers to make sure that the train has cleared. And so now what I can do is I can reverse the direction, bring this back, and now we'll come back through. We'll come back through at a little bit higher speed this time, maybe around 30. And you see it says busy at 36.5. So, and as you see, it's flashing every time because what's happening is the gap between the cars allows the sensor to reset, and then it re-triggers on the next car comes through. Now I'm going to run the train backwards in the other direction just to show what happens, that it does run bidirectionally. And there we are at 28 miles an hour. Again, I'll stop the train, wait for it to clear, because you cannot change the mode while it's in the wait state. So now so 28 miles an hour in HO is 51.5 in N. Alright guys, so that's a wrap for this longer than expected video. I hope you enjoyed it, and if you liked it, please give me a thumbs up, maybe consider subscribing. So keep an eye out for part 2 of this video, where I'm going to take it to the next level as I mentioned, and I think you'll find that pretty cool and hopefully entertaining as well. So until next time, I'm Rick, this is the Switch List, and I will see you down the rails.